So good afternoon, good morning, good evening, depends on where you are in the world. So we are starting now our new season of CASS Talks. So today we have the pleasure to have here Noman Hai from Synopsys, Canada, and he's talking about high-speed wireline interconnects, design challenge and innovations in 224G SerDes. So before giving the floor to Norman, just some brief announcements. So next week we have a talk by Victor Champak from Inahue, Puebla, Mexico. Then in 11 days start the Microelectronics School and the South Symposium Microelectronics in Curitiba. Then you have the Brazilian edition of Cadathlon in July 24 in Maceió. So you are welcome to participate on this marathon of microelectronics. Then SBCCI, the deadline has already passed, but it's collocated with other events that are open now, like SB Micro, WCASS, and the Student Forum. And this year also we are going to do a extension of the conference in a hotel in the jungle. So this is optional, and there we are going to have a panel about the green circuits. So this is a great experience if you have the opportunity to stay some few days more the weekend after the conference. And Verasa SOC 2025 is in South America this time, in Puerto Varas. So the submission is May 16, and there is also some grants for the students that have papers in the conference. So I hope that you submit your paper to May 16. And LASCAS, the Latin America Symposium Sequencing System, so next edition, February next year in Arequipa, in Peru, together with Iberchip workshop. And 2027 will be in Panama. But we are today here to attend the talk by Noman Hai. So he is earned his bachelor engineering degree in electrical engineering from NED University, Karachi, Pakistan in 2002, followed by master in electrical engineering from Linköping University in Sweden in 2006, and the PhD in electrical engineering from the University of Waterloo, Canada in 2012. His doctoral research focused on the development of CMOS analog to digital converters. He has extensive experience in analog design engineering, having held roles in the Philips Semiconductor Eindhoven, Macon, Canada, Movelus, Canada, and Synopsys, Canada. Across these positions, he contributed to the design of high-speed analog circuits for wireline and machine learning applications. Currently, he serves as Senior Analog Design Manager at Synopsys in Mississauga, Canada, where he leads the design of high-speed interface IP circuits focusing on 224 gigabytes per second SerDes development. His research interests span high-speed I/O circuits, design methodologies, and automation and mixed-signal circuit design, and he's the holder of the 3 USA patents. So, Norman, thank you very much for accepting our invitation, and the floor is with you to start your talk.
Thank you so much. Thanks, Ricardo, for inviting me to this talk. This topic is very close to me, and I like to talk about these high-speed wireline interconnects and what are the challenges and innovations we are doing in the highest speed SerDes design. So thanks for inviting me. This is a self-introduction. You already talked about it, so I'm not going to go much into detail there. Thank you so much for introducing me. So this is the outline of my presentation. I'm going to go a little bit more high level and start with what are the interface IPs to begin with, and the different wireline standards we have. Then I will go into the challenges we are facing in our data computing and bandwidth. And that will take us into the philosophical and the circuit level overview, what a SerDes is all about. And and then we will talk more into the actual circuits, which are transmitters and receiver and their important blocks. And we'll try to wrap it up within 50 minutes. And if you have any questions, please put it in the chat. And if you have time, we can take the questions in the middle, or we can finish our talk and then we'll address your questions. So this is our third party design IP market. I'm just starting with a very high level overview, why we care about what we are trying to learn today. So in our SoCs or system on chips, there are different blocks which the SoC companies may not want to do it themselves. They need an IPs from different other vendors. So these are the different vendors, and the different kind of an IPs. For example, a processor IP. We already know about uh, the processor IPs like coming from ARM or ARC processor from Synopsys. There are RISC-V processors too. So they are processor IPs which we sell it and goes to our cell phones, to our laptops. Then we have our foundation IPs. The foundation IPs are usually the memory compilers, the sensors, and the one of the most important, which is about 30% of the whole market, is the interface IPs. Interface IPs are the IPs which connect different blocks together, as the name suggests. And there are different IPs for memory interfaces. So DDR memories and other memories, we have different interfaces there. There are interfaces with the system, for example, PCIe, which we already use. Ethernet, we are very familiar with. The other one is like USB, HDMI, USB. We're already using it in our day-to-day consumer application. And then we have chiplets, which is a very another field, and we call it like die-to-die interfaces. So there are bunch of interfaces in the market, in the industry as well. So Synopsys, this is more like a slide I got from semiconductor website there, SemiWiki. And Synopsys is one of the leading IP providers in the world, and especially in the interface IP, we are the leaders. And within interface IP, the wired IP is one of the growth sector, and it is growing with a very high speed, and similar to the processor category as well. So what we are trying to do is I'm trying to go stay within the interface IP business, or the IPs of the which we use it in within our Synopsys environment as well. So there are different kind of a wireline interfaces. So one of the interfaces on the left-hand side, you can see that we have PCIe, which many of us know. SATA, for example, if you have an external hard drive, we use SATA hard drive to do this thing. USB is pretty popular. You already know DDR memories. CEI is the common electrical interface, which is usually go for an optical and electrical interconnect, the Ethernet ones. And you can see these are the green ones. They are going at a much higher speed. This is a little bit old data from Solid State Circuit magazine, but you can see we are going towards 128 in 2020, and now we have 224 and 448 going forward in our design. And on the right-hand side is more like how it is growing over time. And you can see that the yellow line, which is about Ethernet and die-to-die interfaces, they're growing at pretty high rate compared to some other interfaces as well. So this is just an overview that there are the top 5 interfaces and how are they growing at much faster speed. So I am focusing on this yellow block, which is the Ethernet and die-to-die. And within Ethernet and die-to-die, I am focusing only on the Ethernet part, which is the highest speed SerDes. I have not introduced the word SerDes yet, but let's go with that part as well. So I'm going to start with our Synopsys has a 224 gigabit per second paper at ICC last year, and it was well received. And I'm one of the authors there. There's a huge team in Canada which have done the whole design. So one of my team is also part of the DX. So I'm mostly the owner of the transmitter side. So these are the 224 gig paper we just introduced, and the reason to show that thing is that ISCC is a peer-reviewed paper. So when we present and it was accepted and it's shown on at this stage, it means that people know that the design from Synopsys is one of the best, or the best industry standard as well. So let's start with the challenges we are facing in our day-to-day activities. I use this slide a lot, but what we are seeing here is that over time, the data has been generated is of a staggering amount, and the expectations that are even in this year, at the end of this year, we are about 200 zettabytes of data will be generated. Having said that, the number does not really make much more sense to us if we don't put it in the perspective. So assuming that we have 1 terabyte of hard drive, usually people have 1 terabyte of hard drives. So if we have 1 terabyte of hard drive, then we may need 200 billion of those to just save the data for only this year. That's a huge, staggering amount that you can imagine that it will take huge amount of space. If we just start storing only the data for this year, what about the data from the previous years and the upcoming years? So that's a huge amount. We know the data is generated. Having said that, it's a little bit not easy to understand from where actually this data is being generated to begin with. So this is another slide which is coming from Domo, that how much data is being generated every minute of the day by us. And one of those ones is, for example, you already know Twitter accounts, the Amazons, and the Google searches, the WhatsApps, the LinkedIn. Just go in that one. Like 241 million emails people are sending within 1 minute. We are searching online, Facebook, ChatGPT, we already there, Instagram. So these are few of those social media accounts which you have been using it in your day-to-day activities, and they are the ones who are generating the huge amount of data. One of the data we are talking about there. So now you got some kind of a feeling that from where actually these data is being generated, which we talked about in the previous slide, that we are generating 200 zettabytes of data. Having said that, we realize that generating the data from our social media account, or going in a Zoom meeting, or watching YouTube video, there is still only 15% of the total data traffic in the whole world. And about 14% is between one data center to another data center. For example, we uploaded a YouTube video, and somebody on the other side of the world wants to watch the same YouTube video. So that video needs to be replicated so that it will give us a little bit of an easier access. So that replication data, or the content delivery, usually done between one data center to another data center. However, the most information exchange happen is within data centers, more than 72, which around 72%. This is a little bit an old data from Cisco, but around 72%. So what is happening within a data center, that the data is moving between different racks? And you can think about it. What does it mean? That, for example, if you upload a YouTube video, or it has to be tagged, it needs to make sure they're not violating any copyrights. They do some machine learning algorithms on top of that thing, and all of these things needs to be happen within a data center. So the data move around 72% within a data center. So it means that we need a huge amount of data connection, or we need fatter links to make sure that data can be moved from within the data center. And some of the key parameters we use when we're talking about the data center is the PPA and latency, which is the power, performance, area, latency. And we already know that thing. Power means that we do not want to use so much power that it generates heat, because there's a heat. The electricity is limited within for a data center as well. Performance, we want to make sure that we can do all the things, or all the data transfer in a much higher speed. area is important as well, because we have a limited real estate. We do not want to grow our data centers, so we want to make sure our chips or our racks or our servers are much smaller in size. And latency is very important as well, that everything needs to be done within specific amount of time as well. For example, right now I'm doing a YouTube live, and if there's a latency, you may see the latency between what I am speaking and what are you hearing. And if this latency in this case is okay, because it's okay to get the data in even few seconds later. But what if you are watching a real-time match or real-time game or a hockey game or a soccer game? You do not want to have a delay of 20-30 seconds between a goal and when you watch that one. So let's go into. We already talked about what the motivation behind the Wireline applications there, or the data transfer. So we talk about this concept called what is SerDes. That's what we're going to start about it. So I'll start with the philosophical overview of SerDes. That's I use a lot. So think about it that people are going from, I live in Toronto, and my brother lives in Sydney. So I'm assuming that there are many people going from Canada all the way to the other part of the world. So assuming there are 200 people going, one way is that each of us will have our own jets. The 200 people will go on their own jets. We have 200 runways, 200 captains, 200 crew members. And we already know that doesn't make sense, because it's not only one place we are going. We are maybe going to thousands of places all over the world. And if everybody has their own jet, is becoming a staggering amount. It's becoming not feasible, economically not feasible. Same concept happens in our SerDes or serial communication. What will happen is that rather than sending all the bits in parallel, why not we send them serially? So what will happen that if we do not send them parallel and send them serial, now we reduce the cost, the carbon footprint is better, much less interference with each other too. And at the same time, there's a trade-off as well. Rather than, if I have a jet aeroplane, I may not have to wait in line to get a security clearance, goes through the immigration and go into the aeroplane, and that adds latency into that thing. So when we do a serial communication, what we do is we take the parallel data, pack them together, and send it through one part to the another part through the aeroplane. So aeroplane, we can think that as a transmitter, which transmitting the data serially from one side to another. And you can think that you can make an analogy with a real life, that how this thing matches with our circuits point of view. So same concept, use it in actual in our communication. So rather than having parallel bus where there will be a crosstalks, there will be a clock skew, people will be coming a little bit late. Same thing, that all the aeroplanes, when they fly together, they may not reach at the same time, because everybody will have a different. They may face different kind of a headwinds or a tailwinds or some other interferences, and they may not come at the same time. So that's the skew we're talking about. There will be high pin counts, more wastage of area. Same concept, we do it in the serializer and deserializer, that rather than sending the data in parallel, we send it one at a time, goes through a channel, and then eventually received by receiver, and then parallelly goes to another part of the chip. And what we use a time domain multiplexing in this case, where we send the data at a very precise amount of time, so that at the receiver, they know that exactly a precise amount of time, 1 second, 200 second, 200 nanosecond, or 200 femtosecond, the data is coming, and we already know this coming at exact time, and we are multiplexing the data. So the block level overview. Now we already talked about how it is done, but this is a block level diagram of SerDes. This is a little bit of an old block diagram. This is up to 56 gigabits per second. We're talking about 200, 400, even faster. So this is an old SerDes. We used it in a few years back, like a decade ago or so. But it is a very easy block to understand what is actually being done. On the left-hand side, we have a transmitter, and then on the right-hand side, we have a receiver. And what the transmitter is doing is a fancy way is that it is taking a parallel data and selecting one data at a time and send through the driver to the channel so that it can be received at the receiver output there. So what the transmitter does is it converts the discrete time data into analog data, because the data which goes through the channel becomes analog. I'll come back to what does it mean by channel, but let's hold on the thought for the next slide. And the receiver, which receives the analog data and converts into digital. So we can say that the transmitter on the left hand side is actually digital to analog converter, and on the right hand side is a fancy analog to digital converter. And the channel is the transmission media for the analog signal too. So what is mean by channel? So I'm just giving one of the example. What are the interconnects? We can talk about it. So we can think about it that this green block is a PCB, and then we have two chips on that one, or two package chip. But each chip could also have different dies together. So we can think about it that this ASIC and FPGA is one die, and there is yellow is another die. And we can have a connection between one die to another die, but they are very close. They are maybe within the package, maybe within the same substrate as well, and the connection is very small. So we call it extra short reach. And same thing, if you're going through an optical, we have a different way of calling it. If the chip is going to the output to the optical module, or a connector which connects to the optical module, we call it like a VSR channel. We gave those names such that we know what are the requirements from the receiver and the transmitter for that specific application. You can have an optical cable as well. You can have a twin DAC cable. You can have a PCB traces. And all these channels will have their own requirements for the channel from the receiver in terms of channel losses and the power consumptions and so on and so forth. So they are different kind of application. This is not exhaustive application. This is only small application which is we're talking about within a rack or within a server, which is easier to understand. But there are many other applications as well for a channel to understand. Okay, so we already understand that part. Now I'm going to go into a little bit of detail of a transmitter, and of course I will go into the TX side as well. But before I go, is there any questions from the audience? I cannot see any question, but do you think I could take one or two questions just to see the engagement of the audience?
Or maybe we can leave the questions for the end of the talk.
The end of that. Okay, sounds good.
Okay, thank you.
No problem. So this is a transmitter. So the requirement for the transmitter, as I already mentioned about it, that we have three major blocks when we talk about the SerDes. One is a transmitter, one is a receiver, and then we have a channel. We already talked about the channel in a very quick detail, but now let's go into the transmitter. As I said, transmitter, what it needs to do, it needs to serialize the parallel data. That's the main job of the transmitter. It needs to make sure that we send the data at the full rate. We want to make sure that it can send the data. Full rate means on different application what the rate it is. It should able to provide that data rate. It needs to provide the precise timing as well. As I already mentioned, that we depends on the time division multiplexing. So the data has to be arrived exactly at the same time for the receiver to understand what data it is. Modulation technique means we call it NRZ, PAM3, PAM4. What it means is that rather than sending the data one bit of information one at a time, how about we send multiple bits of information in the same amount of times? They call it modulation technique. We're going to talk about it more. It needs to provide sufficient voltage swing. We can understand so that the higher the swing, it is easier for the receiver to understand what the bits are. And it needs to provide equalization. Equalization, you can compare it with some kind of, as I already mentioned, an aeroplane is a transmitter, and it is going through an airspace, and it is finding some air pockets and the air resistance and other issues, and it needs to equalize. It should not put all these hiccups to the passenger. So it should able to equalize itself such that less amount of turbulence will be faced by the passengers. And overall, and it has to achieve all those above things with low power and less area. That is always an important consideration. So in order to characterize a transmitter, we can have different kind of transmitter, but what is a better transmitter compared to the another one? We usually use the concept of eye diagrams. What does it mean is that eye diagram is, if we send the data through a channel and we will receive the bits which we are supposed to be ones and zeros, and they may not be ones and zeros, and they will look like pretty analog signals. So one way is to look at all the waveform in one shot through our oscilloscope or through our simulation environment, which is very hard to do it. So what we did is that we take one chunk of data, whatever that data is, we usually call it like a UI, unit interval, and plot on top of each other. So rather than seeing the waveform in a time domain for a long amount of time, we just compress them. We give it a snapshot of the whole waveform, and that snapshot, we call it an eye diagram. And this eye diagram will tell us a lot about the characteristics of our transmitter, which we go in the second slide there. That when the eye diagram is when we look at the eye diagram, it will look something like this. It has a horizontal eye opening, it has a vertical eye opening, and it has a jitter around its edges, it has a noise on the top. So this is the eye diagram you see from different transmitters. And why we care about eye diagrams? We do not really care about the eye diagram. What we really care is that if we send the data from the transmitter, it should receive by the receiver, and the receiver should be able to make the prediction that whatever the data is 1 or 0. So the probability, we want to make sure that we have a higher probability that when we send the data through a transmitter, we should be able to receive it with much higher confidence. These are all qualitative measures. So what are the quantitative measures? The quantitative measure, I think I skipped the slide there. The quantitative measure is called bit error rate. We want to make sure that the less bit errors less errors will be gone through the channel or received by the receiver. And in order to do this, we should able to look at the eye diagram and able to predict the performance of the whole link at the end of the for the whole link. The reason we need the eye diagram, because simulating the whole link is not very efficient in terms of time. It will take huge amount of time to simulate the whole link with the transmitter and receiver. So the eye diagrams are usually a very good way to look into the performance of a transmitter. Now I'm going into the modulation technique. As I mentioned, that rather than sending the data one information like the data is 1 or 0, which is, we call it NRZ, non-return to zero data. If we send this data, only one bit of information is present at a given amount of time. But if you want to send more information, what we can do is we can put it more bits into the same amount of time, in this case PAM4 signal. Now you have 4 signals available, -3, -1, and now the receiver has to detect this data and able to make a prediction that what data is what. And it is a little bit hard to predict in terms of compared to NRZ. It's very easy to know if you sample the data here, if the data is higher than 0, you already know is 1. If lower than 0, then you already know is 0. Whereas in this case, our signal to noise ratio get worse, and we add a penalty of around 10 dB if you go from NRZ to PAM4. However, it was a challenge a few years ago, but now this challenge has been removed. So now industry has been working on PAM4. Is becoming an industry standard, at least for up to 400 gigabits per second. Now, one of the other block within the transmitter is called receiver, the serializer. And serializer is just, if you think about it, is just a cascade of muxes. So if you have 64 bit of information coming in, you just cascade these muxes together such that eventually you will get, you select only one bit at a time and send it to the output. So receiver serializer is just a cascade of muxes, and we keep doing the muxing over time until we reaches at the end, and we send the data output there. The final mux, the final flip flop, this is, we call it a full rate mux. I'm not going to go into detail. There are many other ones they call half rate, quarter rate, but this is above the topic of our talk right now. Okay, so the other part which is very important and maybe easier to explain and important, that what is actually driver is. So if I think about it, the last 2 to 1 mux and the driver, like last 2 bit of information coming in, and we need to select one of them and send it out. One way is using a voltage mode logic, or we call it a Thevenin equivalence circuit there. For example, these two data are coming depending on the clock, which clock 0 and 180, because they are out of phase of each other. And we can select one data and send it output. This we call it a voltage mode logic. And the other one is called current mode logic. So rather than based on what clock is coming, we pull that node down, and that information is sent through TXP and TXM to tell us that what data is present. This is called current mode logic, and this is called voltage mode logic. And what the current mode logic will look like is just a simple diff pair. Uh, in this diff pair, assuming we have data P is coming as positive, N is coming as negative, what will happen is this NMOS transistor is off. So the whole current is flowing through this transistor. And when the current flow through this transistor, there are RT, we call it a termination resistance. So there's one RT, one path for the current to flow from there all the way down. And there's another path from this RT goes all the way to the channel and to the termination resistance of the receiver to the back. And then that will create a different voltage across V out. And for different data rates, or data inputs, we can get two different kind of outputs. So that's how we got our NRZ I diagram, put like that. And the swing is dictated by the bias current and the termination resistance. And the power dissipation is VDD times the R bias. This is just a simple simulation. You can see that it does not look like something fancy. We can use our custom compiler from Synopsys tool. Just put this circuit diagram into that one, and you can get a pretty reasonable I diagrams, which we are talking about. So it's pretty straightforward that we can use a simple CML logic and get an I diagram too. And the same concept, we can extend it, make it look like a PAM4 signal as well by using an MSB and LSB as well. Now go into a voltage mode logic. Voltage mode logic is this one is the same thing. Rather than sending through a current, we can use a simple inverter. And in this case, we have a single-ended termination, and in this case, we have a differential, and it has its own advantages and disadvantages as well. The practical circuit, we call it like SST driver in a voltage mode circuit, because as we know that inverter itself does not have the proper termination resistance. So in order to make it proper termination resistance, we put a termination resistance in the source of the NMOS and the PMOSs as well, and thus we call it a source terminated, such that the overall total impedance is RT plus RZN, which is the impedance of the NMOS, should be within 50 ohms. And this is a practical way to do an SST driver. And you can see, if you can just do a simple SST driver, you will get a nice I diagram too. One other aspect of the TX, we already mentioned that assuming we already talked about the serializer, we already talked about the driver. There's another concept called FFE. FFE is called feed forward equalization. So what we do is that rather than sending the data as is, we pre-distort the signal because we already know that when it goes through a channel, and channel does have a low pass response most of the time, and if we go to the low pass response, can we not able to invert that characteristic there? So this is one of the ways we can do in FFE. FFE is like you delay the data and combine them with some weights. In this case, an alpha for different weightage, and we delay them and combine them such that we send a distorted or pre-distorted signal through the channel. So here is an example. So if you can see that on the bottom we have a red dashed line. If we send this input data, you will get a blue output, and this is our waveform after the channel. And you can see receiver has no information because the eye is closed. It has no idea if the data is 1 or 0, which is pretty difficult for a receiver to work with. So one way is that since we already know what kind of a channel it could be, we can pre-distort this channel, and this is what we're showing here in the blue curve. And if you put it on the blue curve, you can see that the output of that one is this brown line or a red line or eye diagram there. As you can see that our eye is pretty open, and it is very easy for receiver to detect whether the input is 1 or 0. But at the same time, our swing is reduced. Previously, you can see the swing is from 0 to 700 millivolt. In this case, now it is between 250 to 500 millivolt. So we reduce the DC swing, but we increase the swing of the high frequency content. And that is the main job of an equalizer. What is the main job of an equalizer? The main job of an equalizer is to make sure that the frequency content of, the amplitude of the low frequency content and the high frequency content is the same. And when this thing happens, we will get a very nice equalized eye. And this is the coefficients we got it. And we already know from the previous slide that the coefficient I'm talking about is the previous alpha values there. And how do we get these coefficients? Usually we use an optimization algorithms, especially we call it a minimum mean squared error as well. Okay. So as I mentioned in the beginning that this is analog-based TX. It has been used up to 50 gigabits per second transmitters. But when we go to 100 and beyond, what we realize that rather than doing all the complicated PAM4 equalization and FFE, we can do all these things in our DSP, which is more easier to deal with in a lower technology nodes. And then we have a serializer, and the DAC and the TX will be used as a DAC. So the digital input is coming in, and we are converting that digital into analog at the final stage and send the data. And it proven that over last for more than 100 gigabits drivers, more than 65% are the DAC or DSP based. And this is one of the implementation. If you read papers, or even if you read our papers as well on 224 gig or beyond, you will see this is the transmitter architecture. It looks complicated, but it is not. As I mentioned, we have a DSP, then we have a serializer, which is a cascade of muxes we already talked about. Then we have a final driver, which send the data output. But before that, we need to generate the final pulse, which is the output going in and going to the driver. And driver is usually have some kind of a T coils to compensate for the losses coming from the ESD and the capacitance and the pad capacitance and the termination capacitance, so on. In order to make all this thing work, we need a multi-phase clocks as well, which is another topic, and so on and so forth as well. So I'm going to go fast into the receiver part. So we already talked about this is our TX will look like. We send the data from the TX eye diagrams looks very nice. When it goes through a channel, and I'm showing you one of the channels there. I'm just got this thing from online, that a channel could be anything. So for example, the signal is going through a daughter board, through a connector to the motherboard, goes through the whole motherboard in the PCB, and it has another connector. So the crosstalk reflections and all these things will come up. And you may see that eye diagram after the channel is kind of totally closed. We have no information what it is coming. And here the receiver comes in. The receiver has an equalization part, and it should be able to recover some of the data. You can see the eye diagram, eye is not fully open, but it should be able to open up as much such that our slicer or comparator can able to detect that what kind of a data has been sent by the receiver. So the receiver has a very important role to play here. So as I said, receiver need to deserialize the incoming data. This is also important part. One of the main properties or main job of a receiver is the equalization. It has to work at the full rate because full rate data is coming in, and it has to maintain the precise timing because it does not know when the data is coming, so it needs to recover the data as well, and it has to work with the low power and low area as well. So this is a quick summary that this is our power efficiency of receiver over time. So when we started many years ago, so we usually use the CTLE. Then we go into when over technology limits or with the better processes, we are doing half rate DFE. Then in 2016, we are doing mostly speculative DFEs as well. Then last 5-6 years, we moved into ADC and DSP based and with the forward direct corrections and so forth. And nowadays MLSD and beyond. I just added these lines myself because we are now into 2025 and moving forward. So you can see that they are talking about in 2024 is like 100 gigabits per second, but we are now talking about 200 and even 400 going forward. So let's go into some of the blocks. One of the main block is the CTLE, which is called continuous time linear equalizer. And as I said, I already mentioned when I was talking about FFE, the CTLE is the main function is to bring all the frequency components of the signal to the similar amplitude. So the main job is if you have a high frequency, that swing should be similar to the low frequency. And what we do is we usually do it using a de-emphasis. So rather than boosting the high frequency signal, we reduce the swing of the low frequency signal, which is done through a CTLE in this case there. And inverter-based CTLE, which we have used in our 224 gigabits per second, becomes much more prevalent as well because just simple inverters. It's much easier to control as well, and it is good with the process and technology too. Of course, it comes with its own challenge as well. But there's one interesting thing that one of the conferences I was there, and there's a big professor there, and he was mentioning that eventually, when you start looking, everything looks like an inverter, which is very true in this case. So CTLE will do a continuous time, and then we can go into the next stage of the time in 2008 when we use the DFE. What the DFE does is it's a decision feedback equalization, something similar that you take the data output, and in this case, I've made many taps, but you send this data back and correct the ISI from the upcoming data there, and subtract them directly, such that you subtract the ISI right away without adding noise into the circuit. This is our full rate ADC, full rate DFE. As you can see, the output goes through a weighted and subtracted from the next symbol. But this is our critical feedback because the data has to go all the way there within 1 UI time frame, and that can be relaxed using a half rate DFE. So you can have a half rate clocks, and it gives you more time for the data because you're taking the data from the previous from the N side going to the P side, and so on and so forth. One other concept is called speculative or loop unrolled. This becomes very popular in last 10 years as well when you use the DFE, is that you do not care whether the data is 1 and 0. You just assume that one data is for sure is 1 and you assume the data is 0, and you select them at the end. But at the end of the day, it's you're selecting, but this is still one of the main bottlenecks, this loop to control. Rather than subtraction part, you remove the subtraction part, but the muxing part still stays the same. But the speculative DFE becomes very popular as well. However, nowadays, because we are working with the PAM4 and many other issues, we decided last 5 years that after 50 gigabits per second, the ADC based receiver is much more useful, because once we convert this analog data into digital, all this information we can correct it in the DSP. So most of the heavy lifting now goes to DSP, assuming our ADC does its own job very well. So the ADC has the DSP does few things. We do FFE, similar FFE like receiver. Right now, when we reach to the FFE, the data is already into digital domain, so it's easier to do the feed forward correction. And we also use sometime DFE as well. Same concept, like analog DFE. The other part, which is becoming much more important as well, is that with the high speeds and also with the signal integrity and other challenges, we cannot able to meet our BER requirements. So one of the ways is to mitigate is using MLSD. It's called maximum likelihood sequence detection, and it has been used quite extensive in the wireless application. But the concept is pretty simple. Concept is not that difficult. It's like rather than seeing one bit of information, you look at series of data, and when you look at series of data, you can able to predict that from what are the possible stages or branches this data should have come, and we select one of the branches which is much more likely to happen given the data is present. So, and we usually use Viterbi algorithms to find out the MLSD, and it is a topic in itself. However, this MLSD is pretty complex and power consuming, and it has been used sparingly in designs less than 100 gigabits per second. It's usually more important in optical and have more than 200 gigabits per second as well. So I think I'm on time. We are finishing. This is the era we are talking about, starting from 200 year 200s. I did my undergrad when I did. It was called PCI-X. I did a microcontroller in 2002, not 2002, 2001. At that time, it was parallel. PCI-X was a parallel combination, parallel circuit. There was no serial PCIe at that time as well. But you can see that from 2000, things have grown up like crazy. We have seen 28 gigabits per second is a very inflection point. And after that, when we go into 56 or more, PAM4 starts to come in. We are now in 24 gigabits per second. It's been in history now. It's been there for 3-4 years. Now the next step is 448 and so on and so forth. This is one part, and there's another topic going on that this 28, when we reach there, why not we continue on 448 in Ethernet side and optical side, but what about at 28? We stop there. We say, okay, NRZ is really good, but why not we go more parallel? So cycle is repeating for us, and I was there as well when we go from parallel to serial. But it looks like that there are some applications where the parallel data or the parallel SerDes will become much more prevalent going forward, including UCIe and bunch of wires and other standard, which is more becoming popular due to chiplets and the packaging technologies and so on and so forth. This is a topic in itself. Okay. So these are the few references. We had our, just a couple of weeks back, CICC, I was one of the speakers there. We talked about our 224 gig design. I was part of a Circuit Insight talk with the students. Similar topic I covered there too. Some of these ones, I have also done a tutorial on wireline transmitter. This is a 3-hour tutorial. So if you want to go more into detail about how the transmitter is working, what are the details we need to care about, this has been you can see it. This on available on Synopsys website as well, and so on and so forth. So before I go, I want to talk a little bit quickly about the Synopsys tools we have. Many people do not know much about our analog or custom tools compared to our competitor. But our tools are really good. These are the tools we use, and we are doing quite much work on our 224 and optical and other designs too. So custom compiler is very important, and the prime sim is a simulation tool. And these are the things we talk about. And within prime sim, we have different kind of environments. There's a prime sim spice, which you already know. There is spice version, which is our legacy HSpice version. XA is used for the mixed signal and EMIR and other cases too. We also have electro-optical co-design being done as well with our tools. So if you want to know more about our tools, or if you want to use it in your universities, if you want to try, I think you should talk to our product management team. I added his name there as well. And just simple thing. We also have a 5 spite, and we can use with our some of the GPUs the time to time performance is becoming much better. The speed up is huge with when we use the GPU with our tools as well. And we also have a different factor called like a fast spice, which can able to use a lookup table, take a huge design, put it into small chunks, and send different data to different GPUs and speed up the design quickly. Thank you so much. I think I'm on time. Thanks for listening. So I can take some questions now.
Yes, thank you very much, Norman. So we have
I
for
think
the moment
Mhm.
some questions here. So first one by Pedro Toledo from Synopsys, Portugal. What is the Nyquist rate in the state-of-the-art SerDes?
so when we say state of the art SerDes, so right now is a PAM4 of designs we are using, going hard more than 100 gigabits per second. So you can see that for 200 gigabits per second, the Nyquist rate is 56 gigahertz. So that's how we can do this. Because if it is 224 gigabits per second and is a simple NRZ, the Nyquist rate will be 112 gigabits per second, just half. But since we are using PAM4, is 1/4, and that's one of the main reasons we go for PAM4, so that we do not cross the Nyquist limit of more than 50. Because after 50, even in a normal channels, you will start seeing reflections and other imperfections coming in.
Okay, thank you. So now a question by Mas Kurham. Hi, Norman. What are some of the major analog design challenges and likely solutions for 448 gigabytes per second and beyond connectivity?
So I think 448 is similar challenges we faced few years ago for 224 gigabits per second. Same issue now. When we go for 448, you can imagine now the Nyquist rate becomes 112 gigabits per second, and exactly the same thing I mentioned, that the signal integrity, power integrity, and all those challenges which are usually not we care about becomes much more of a problem. So and the capacitance and and all the termination part, everything becomes very critical, because at 448 gigabits per second, you're talking about femtos of seconds of jitter to tolerate. So everything becomes twice more difficult. So challenge will remain the same. Whatever the challenges we face in 224 gigs, it's just 448. But I think with the proper understanding of the technology, because the technology and the processes, we should able to meet 448. I don't think that's a beyond our reach. Okay, Ricardo, I think I
Thank you.
Okay, you are there. Okay.
So I have another question from Mas Kuham. What are some of the differences in transfer function of FFE and the CTLE?
So
It
if
seems like both blocks boost high frequency content to counteract the effect of low pass profiles on
Okay, I think Ricardo, you're breaking up, but I got the question there. So I think the question was the difference between FFE and CTLE. FFE, when you're talking about, I believe you're talking about the TX. The problem with the TX FFE was that you sometimes you do not have the channel information as the much as or the CTLE knows. So FFE has its own drawbacks because you cannot add too much FFE coefficients. The reason is also that in FFE your maximum transfer is limited. You cannot go beyond the swing of the driver. If you use more FFE, the DC swing reduce. So now you're reducing the swing such that you can get. You already saw my slide there, and when once that thing happens, then of course the swing gets reduced. Whereas CTLE also does the same thing, but CTLE has more information about the channel and it can able to adapt with the different with the capacitors and resistors and able to mitigate. Whereas CTLE also boosts the noise because it has no information about the low frequency, the noise and the signal. So any high frequency it boosts as well. So it boosts the noise too. Okay. I don't know
Okay.
if it answered the question. Mhm.
A question by José Batista Salles from Synopsys, Canada. What advice would you recommend to students and young engineers to start analog design career in SerDes?
Exactly. I think if you see my slides, I pay a very important emphasis in the slides as well. That the slides look very easy to you. They all look like that. These things are I already know. It's nothing magic happening in the 224 gig. It's just the basics. If you know the basics done properly, and the basics means like second year, third year, or early grad school analog courses, if you really understand those courses, everything is just the manifestation of those understanding. So as long as you have a good understanding of analog basics, how inverter works. And you cannot imagine, I interviewed so many people and they do not even know how inverter works. That's a sad story. And if you understand how inverter works, then the next step is how the current source work. Then you go to the next level, how we can connect these things together to create a CTLE, how the resistor work, how a capacitor works. Nothing magic. Everything is very basic. And if you understand the basics, maybe if I ask question, what is an inductor? Many people will not able to answer. I can guarantee you. What is an inductor and don't give me an example about this acquire and this thing. What an inductor in a chip design and with what we see that thing. So that is a very important thing that you understand the basics: resistor, capacitor, inductor, inverter, NMOS, PMOS. If you understand those things, that's the best way to start your analog design career journey, and and you can go much farther ahead with that thing too. Nothing fancy.
Thank you. Have a last question by Mas Kuham. Is there a reason some of the recent Internet solid state sequence conference papers report 212 gigabytes per second instead of
Yeah,
standard 224 gigabytes number?
yeah. This is IEEE standard there. So I think there's an Ethernet standard, and I think there's an OIF standard. It's just a standard. So we usually use 212 a lot as well. But 224 gig is also common too. It's just a standard.
Okay. Another question by Anna Gaboyam. Thank you for the lecture. I would like to know what solutions are available to avoid the level dependent nonlinearity, for example, at middle levels in PAM4 when using FFE.
Okay, that, yeah, it's a very loaded question. So I don't think I have an answer to that in that small amount of time. But so when we talking about the non-level dependent non-linearity, you want to make sure that all your eyes are exactly the same size, and it has a very it's a complicated problem. You need to make sure your DAC has a proper linearity as well. And if your DAC has a proper linearity or a very good DNL, then FFE should not able to um, should not have any. If that is a question, I would like to know what solutions I will avoid. Yeah, so you should not get if you have a very good linearity within a driver. I think you will be able to avoid the these RLM issues using FFE as well. I don't know if it answers your question or maybe she may have some specific uh, question in mind.
Okay, thank you. So I see no more questions.
Okay,
So thank you very much, Norman, for this very interesting talk. And
thank you
I
so
hope
much.
to see you in person in the near future. And
Sounds good. Thank you so much.
so before closing the session, just to remind you that next week we have another CASS talk by uh, Professor Victor Champak from Puebla, Mexico. And so we have many others that we will announce soon. Thank you very much for all you that attended this very nice presentation from Norman today, and I hope to see you next week. So bye bye and
Thank
have
you.
a nice weekend.
Thank you so much. Thanks for
Thank
having me.
you.
Bye.